Hello and welcome. I'm Derrick Dasenbrock in Minneapolis, Minnesota, and my co-host today is Ben Rivers in Atlanta, Georgia, and we'll be tag team moderating today's exciting winter webinar A-GaME season finale, webinar 10 of 10. As we start, I'd like to take a quick look back at the winter season. We began on November 17th after an unexpectedly long off season with several Zoom webinars. We started out the season with Welcome Back to the A-GaME, the second half, then talked about selecting the right tools for the job and establishing the project goal and the path to get there. We continued with contracting and how to assemble a winning A-GaME team. And then webinar 4 was about outcomes, how to win your A-GaME. We then had a number of specialty sessions on the topics of geophysics, particularly electrical resistivity and seismic methods, cone penetration testing, measurement while drilling, acoustic and optical televiewers, and then a discussion about processing and analysis last week, which brings us to today's webinar, the winter webinar blockbuster season finale on reporting and visualization and the big picture for a winning A-GaME season. So we'd like to welcome everybody today, live February 9th, 2021. Today we're going to be covering a number of interesting topics, the value of big data for risk mitigation, looking ahead to EDC 6, Federal Highways Initiative about digital plans and as-built drawings, talking about Ohio's experience with the benefits of DIGS for communication of geotechnical information, then a discussion of data visualization and augmented reality, to the conclusion, some deep thoughts on added value of A-GaME technologies and other related items for us to consider and ponder as we move forward into the post-GaME season, which brings us to what's next for the A-GaME. As I mentioned, I'm going to be co-hosting with Ben Rivers. We're both with the Federal Highway Resource Center. Our speakers today, Vanessa Bateman from the Corps of Engineers, David Unkefer with the Resource Center, also here at Federal Highways. Even though I have the pronunciation for Steve's name, I'm going to work at it here. Steve Toliver from Ohio DOT, Scott Anderson with BGC Engineering, and Alan Marr with Geocomp. So with that, we're going to get things started. I'm going to stop my screen share here and invite Vanessa to share her screen as I introduce her. Vanessa Bateman is currently the Chief of Civil Works Engineering at the U.S. Army Corps of Engineers. She has over 25 years in the field of geology and geoengineering. Working both at Tennessee DOT and the Corps of Engineers, with a history of working on practical aspects of using data and new technologies to support project assessment, design, and analyses. She has background in geotechnics with particular interests in rock slope engineering, grouting, karst, and dam safety, working on many large dam projects such as the Mosul Dam grouting, Wolf Creek Dam safety modifications, Center Hill Dam safety modifications, and the OC River rock slide. So with that, Vanessa, the screen is yours.
All right, thank you very much. So you're going to hear a lot about data today and visualization. And one of the things I wanted to do as we're going through this is talk a little bit about kind of where some of this comes from and how it relates to risk mitigation. So all of the tools and techniques you're going to hear in this presentation, you're going to hear how you can push these even further with some of the later presentations. But also, of course, one of the things you've been hearing on these A-GaME presentations is all of these wonderful tools and techniques that create actually quite a bit of data that we need to be using effectively on our project. So, my first question for you is, what information management system are you using now? Right? We all probably have things on our computer desktop. We have old drawings, whether or not they're done by hand or done in CAD. We keep things in file drawers and filing cabinets. This stuff is great. But the issue is, how can you get all the data that you need for people to be able to see quickly? If you've got 10,000 grouting records, let's say, to sort through, how fast can you do it? And how fast can you actually find the information that you need in order to actually be able to effectively make some judgments on your projects? What's the format of your data? Did you have to manually draw it on your plan sheets, right? We've got our friend the snail over here kind of helping us out with that, because sometimes it really can be a very slow process from the manual generation into our data systems. And unless you're getting your data into a format that you can use and visualize and analyze quickly, you may not learn some of the things that you need to know about some of your projects. We have CAD drawings, right? We've got BIM that's come into play, but an awful lot of us are still using kind of the old style. Really, we're not drawing them with rapidograph pens anymore. We've got a computer program, but how many of you actually draw your boring logs on the plan sheets? And I suspect what you'll find is there's actually quite a few people who still do that. So you've got a lot of good data. How can you compare it with other data? And that's one of the reasons why you need to be thinking about your data holistically and approaching this all as a whole. Just to kind of bring it home to something I know all of you have to deal with, how many borings do you have in your agency? Can you find them quickly, and how much does it cost to replace them? Because I think what you'll find is it's a heck of a lot more expensive than you might actually originally consider. So doing things like organizing your data and having a boring log and lab database save money. It absolutely saves money. Now, it's always hard for us to get it from paper into the computer program, but what is the cost of actually not keeping this data and actually, losing track of it? And I know many of us have had the experience starting on a brand new project. It's a widening, it's a new bridge, it's a modification, in my case, to a lot of projects to a dam. The experience of not being able to find borings that you knew were there, right? That's a big risk to your project, and it's a financial risk to your project. You're not as responsive. You're not able to actually do some of the things that you need to do. So this is just one project, and I have 120 plus borings shown on this screen starting from 1943 that we actually use for risk assessment and for modification design. So how fast can you find that data when you touch the project again, right? You're going to waste a lot of money, so that's a financial risk. With your organization, if you can't find this data and communicate it effectively to everybody that needs to do that. So when we're doing a risk assessment, let's say, I don't want a whole bunch of engineers sitting in a room saying, oh, well, we're not sure if we have a problem over there. Can't somebody find the borings, right? I get expensive folks with high power engineering knowledge. I need them focused on doing the work. I don't need them focused on, oh my gosh, where can I find all my stuff? And so just a quick example for replacement cost. This particular project, just the borings shown on this screen, it's not even all the borings on this project. If we were to have to replace all of the 120 plus borings shown on this screen that we drilled from 1943 to 1977, it would cost somewhere in the neighborhood of $495,000. That is a lot more money than you might think. Okay, so that's a dam, and you're thinking, oh, well, we may be from a transportation agency or whatnot. You guys do a whole lot of work on one of these individual projects. But so how many bridge foundations do you have within your state? If you're from an AE firm, how many bridge projects do you work on year after year? How many times do we widen these projects, and what's the condition of these foundations? This can be critical and really important information to have together before we get into a project. So this was not one of my projects, but it is at the Tennessee Department of Transportation, and I pulled this from a newsletter that they put together in 2016, and here's one of the key facts I want you to kind of focus on. It included 38,770 feet of pipe piles. So this is a large old bridge. They had to put in 38,000 plus feet of pipe piles. Did you want to have to go redo all of that work again, right? We want to be able to get all of the data we have, bring it together, put it together with our design in our design process, because right, how much time are we going to add to widening projects replacing data that maybe we already had? So one of the most key things you can do when you're working on data management and dealing with some of the data issues that we have on our projects is simply organizing yourself, figuring out where you've put everything and being able to put it into a system where you can make it work effectively for you. So just an example, let's say, okay, we've got a project somewhere. This is just a few of our boring logs scattered from across the United States. I'm going to go around the area in Missouri. I'm going to click on my project. I get to it. Now I have all of my boring logs. Okay, so now when I'm doing a risk assessment of my project, I can get to these things, which tells me a lot about the subsurface and how effective maybe this particular levee is going to be at its job. And if you want to do a risk assessment of a project, it's always the same rule we use with computers, right? Garbage in, garbage out. If you don't have good data to back up your assertions, you're not going to necessarily have the best conclusions. Okay, well, let's talk about instrumentation, right? We use that a lot on our projects. This is actually an example project. This is Chickamauga Lock. So you can see that we've got these nice cofferdams out, we've got it in the middle of the river, and we're excavating the rock. So the stability of these cofferdams, as you might imagine, is of extreme importance to us. A financial risk there, right? If you were to lose one of these cofferdams, it would be very, very expensive to repair everything, get the water pumped back out, replace all of the equipment that you see. It would be a life safety problem, right? Because there are people working inside this pit. And then we are also simultaneously blasting. So we've got a lot of instrumentation actually on this project, and you are going to want to know, hey, if we're blasting down here on the wall, let's see if I can make this show, this pin right here. If we're blasting down here, what's going on? And are we seeing even slight movements in our cofferdam? Because we're going to want to be able to address any issues or any developing issues we see. Okay, so again, how fast can you get that instrumentation data in the middle of construction? I mean, as you can see, as this project has progressed, here's the actual rock wall. Here is the cofferdam. We've got people standing right here. So this is not a situation in terms of financial risk or life safety risk that you want to have slowdowns in getting to your data. And the other question too is, how fast can you check all of that against problematic geology or other construction data? It's all well and good just to have just the instrumentation or just the boring logs, but can you correlate what's going on with your project with all of these things? And what we found on a number of ours is that we've needed to do that, right? We've got a lot of pieces and parts, a lot of things going on. We've got geology that may present some specific kinds of risk. We've designed against those risks. We monitor against those risks. But if you do either of those things, right, you also need to be making sure that when you're monitoring against those risks, that everybody is actually getting the information communicated back out to them as well. And I can tell you from experience, when something happens, even when it's small, you can really get people's attention anytime that we're involving issues that incorporate life safety. Okay, so that's a lock, right? My projects aren't that big. Why do I need to use all these data management tools? This is one of my projects from quite a while ago now, a sinkhole in the middle of I-24. Well, and here's a picture of another one, and this is why. How many of you have found an old project inside a new project, gone out to do a sinkhole repair and found the old one? Did anybody have an inventory? Did we know where this was located? You know, it's fine. We're going to make a fix, but it would have told you something about the risk of that project ahead of time if you had realized that there was an old sinkhole repair there. So you don't always know ahead of time if we're not tracking these things, we're not actually paying attention to where these things are, or if we are, but it's in a file folder somewhere in the back, you know, out near the back dock, and nobody gets into that file folder again. All right, just from another emergency management type of situation, do you have a rockfall inventory? When was the last time maintenance was done on your slope? What are the risks to the traveling public for that? Do you have a program and you can come say, look, we're working on what sites we can get to, you know, we're making good engineering judgments. Is that kind of, is your program defensible? And so again, if you don't have all of this stuff organized, if you haven't put it together and you, when you into these kinds of maps, how do you pick the most effective site to repair? This is actually the Ocoee River Gorge, and this is the site actually that had the big failure in 2009. And my question to you is, if you don't have this information at hand, how fast can you get that data in the event of an emergency, right? How do you know how quickly you need to respond to some of these things? And this is the kind of information that can really help you a lot in a problem. Lots of our construction equipment comes with automated monitoring. Are we looking at that data? Because all too often, only parts of our organizations are. And this is some hugely valuable information that we can use. Are you leveraging GIS, right? There's a lot of visualization tools. And Scott's going to show you some even cooler ones here at the end, later in the presentation. You can do a lot with visualizing old plans. In this case, we were looking at a risk assessment for J. Percy Priest Dam, and it was looking for seepage paths across an area right here. And so what you see in red on this side is we had actually cleaned out karst features and put concrete in it. But on the downstream side, they were cleaned out originally and only backfilled with concrete. And that was directly commented on the risk that we have on the project. So we wanted to make sure that we were actually looking at this in 3D and communicating this to everybody. Okay, so this sounds hard, right? If somebody starts talking about all of this data management stuff, it's like, oh my gosh, it sounds so difficult. Well, let's talk about where we began here at the Corps of Engineers. Really began with this in earnest. A Wolf Creek Dam, it's 6 million acre feet, and we put a seepage barrier wall through the dam, 275 feet down into the karst foundation. So this was a very high profile project for us. This was an absolute no-fail project for us. And this was one of the first times that we put together a really systemic data management system that we used all the way through construction. This is 980,000 square feet of a seepage barrier wall, right? This is a lot of information that we had. And our work platform looked something like this. Right, we had people working on a number of machines, doing a number of different things. We had instrumentation, and this is a very invasive procedure. So we wanted to make sure that we were being very careful with what we were doing, and we were correlating all of the data that we got. So when we're doing this kind of thing, we need to be able to see what's going on with our instrumentation and what does it mean. And just to give, with the deal with the tsunami, we had 71 million records actually on this project. If you printed out just the barrier wall reports, it would have been 144 feet high. And so we really leveraged GIS with this. We leveraged databases with this. We looked at the underlying top of rock contours in relationship to where we were putting in the barrier wall, in relationship to old failure indicators, old seepage distress indicators from previous years. We looked at each individual pile. So these 50-inch diameter piles had to go 275 feet in depth and approximately about no more than 4 inches of deviation per pile. So we leveraged our systems. We took information from the drilling equipment itself and actually put this together in GIS where you could look at the sections at different places along that excavation, and you could see how much deviation you had right on the screen. We did a lot of analysis with all of this, we did grouting on the project, looking at the deviation from the equipment, making sure that everything was meeting our specifications, and assessing the risk of what we were doing every step of the way. So this was hugely helpful to us. And lastly, it really helped us a lot because at the end, we had to do a post-construction risk assessment to make a decision about when we could raise the pool again at Wolf Creek. It had been down for about 7 years at this point. And we had to do that 6 days after we had after we completed the last pile. If you don't have a data management system, if you haven't been doing these kinds of things ahead of time, there's no way you can compile that information and effectively present it within that time frame. We've done a lot of this at Mosul Dam, right? So this was an installation of a grout curtain and an anhydrite and gypsum foundation. So you can imagine that gets to be a little bit of fun. If you've been to a previous presentation, you've probably heard a little bit about this from one of my colleagues. A lot of grout holes, a lot of data, a lot of grout, and a lot of instruments. We actually had about 500 instruments out at the site, so quite a bit. We had automated grout monitoring in the gallery itself, and we needed to be able to know what's going on with the drill, what's going on with the grouting itself, and what's going on with the instrumentation. Because as soon as you see a drop like this, and it's that immediate, you're going to really get people to make a big, everybody's going to want to know what's going on your project right now. Okay, so imagine getting data from 500 and something instruments, including all of the grouting data, the INSAR data, field observations, and more, and not organizing this, right? What happens at that point is you're overwhelmed by the tidal wave. You're absolutely overwhelmed by the tidal wave, and it becomes impossible to keep up with everything. So I've got a quick little video here. This is actually some water coming up out of the foundation. He's trying to cut it off there. But this is what it feels like when you're coming into these very large projects and you haven't gotten everything really put together, right? You're just trying to get control of the water. You're trying to deal with all the data that's coming, the point clouds, again, all of this construction data. And hey, we got it. So we're ready to roll. Okay, so it's a lot of data. And so my point really is, as you're trying to deal with these things, the hard part, honestly, the hardest part is getting it into the database in the first place. Because once you've got it into a database of some kind, whether it's a spatial database, a SQL database, or an Oracle database, whatever it is, whatever tool you're using, you can leverage that in ways that really you never could have done if we were still back in the days of pen and paper. What we did is we had a server side situation, we had maps and cross sections we delivered to people, and then we also delivered web viewers to make it easy for folks to be able to get to the data. So we had navigation tools, we could get around on our map, we had search, measuring, and some annotation, which actually helped, and printing. And then we could click on, like in this case, this is where all of the pictures were. They're geolocated. You just click on the picture, you could bring it up, you could actually share that easily with others, and that turned out to be extremely important as we were dealing with a very dynamic site and dealing with folks spread from Iraq to Alaska. With putting this again in GIS where we could visualize this, that good data flow really helps us to do some really complex analyses and mapping. And in this case, we were actually looking at all of the old grouting that had been done underneath the dam during original construction, where it showed that there might have been additional problems, and cross-correlating that with the grouting data that we were doing on the current project, and also what was happening with the instrumentation. It allowed us to do some more advanced statistical analyses, right? This kind of map is very easy to produce once you have everything into a database. It's extremely difficult to produce if you're trying to, go through 10,000 something grouting records by hand. So, and again, we also put things in kind of a cross-section GIS where we could say, okay, let's show all of our grouting things going on beneath the dam. Red is more grout take, green is less. We can compare that with the historical data, right? Excuse me, well, I'll show you that in just a minute, but we could actually click on the grout stages themselves and get some very detailed data about what was happening. But the other thing that we could do was actually compare it to some of our historical data. So this is some of the water pressure tests that were performed early on in the project, and we could assess things about the geology, what was happening, because it's a very dynamic system, what was happening in the geology from what we knew from original construction to what changes we saw when we got out to the project and we're doing the more current grouting project. And then we looked at things like cavities from historical logs, and you can easily just turn things on and off, right? You can say, okay, this is what I want to look at. No, I want to look at the pressure test. No, I want to look at the cavities, and it's all very easy to do. And again, we had to share this information across about 11 time zones. You just simply cannot do that if you are dependent upon paper or even just email. And then again, you can leverage all of this to be able to see and be able to visualize a lot more into the future. Putting things in 3D on a 2D screen is great. Man, 3D and 3D space is one of the most amazing things I've seen recently here, developing as tools that we can use. So there's so much that you can do, but all of it comes from, I have my data, I organized it, I put it into a database, and then I was able to leverage all of these fabulous computer tools to do analyses, figure out what's going on, figure out what the risks are of my project, and then go about intelligently addressing them. So we started on a project basis, right? We started from Wolf Creek Dam, but we started with the idea of building a program, coming back and saying, hey, we have all of this information, and we don't want to just lose it after the project is done. We want to actually keep using it. And so this is one of our smaller projects within the Corps, actually, working on these SimDAMS models. This just shows you an inventory of a few of them that have been done to date. And then we just developed a schema, the database structure, by working on actual projects, figuring out what we needed. So you don't have to start with this idea that everything has to be perfect before you can actually move. Get started. Start building these things a piece at a time. You'll learn the lessons you need to know, and you can apply them more and more as you go along. And you'll find that this feedback loop actually really helps you quite a lot. So this is another picture back from Addicts Dam. This actually shows a number of different construction features. It shows some of the original construction. It shows where we're actually storing a little bit of soil. It shows where we're putting new features in and where they're going to go. You can see those in relationship to the actual photograph of the area. You can explore these things in detail. And as the years have gone on, we've added more and more to our various information management systems. And one of the biggest things that we're doing in the Corps right now is just trying to make sure that all of these pieces and parts can talk to each other. Because it really helps build our capacity. So this is just an example of some of the inundation mapping that we have available on a number of these projects. You can imagine if you are a dam owner where you're going to get inundation in a particular size storm is hugely important for assessing risk. And now, instead of it being buried over within an H&H department and you're just like, okay, well, who do I have to call this time and who's done it and what time is it updated? I can go into a web viewer. I can see exactly how old this is, and we can use these immediately in risk assessments in the middle of events, or when we're just going through our normal risk assessment cycle. We can take them into our models and say, okay, well, here's all this other stuff going on our project, right? Again, we got the little pictures here for photographs. We have a number of different features on this project, and I can click on the features. So here, I'm just going to take a quick look at a spillway. This is just some basic information about it, but I click on that, and boom, I've got the plan sheets. So now, again, everybody who needs to see this data can see it, and can see it rather quickly. So we don't have to depend on, did I send John over to such and such site to go check to see if they have the plan sheets? We've got them, at least on some of our projects, certainly not all, immediately available. So, and just a couple of points here at the end before we get to questions. Some basic lessons learned on this, really. You do need a data management system, not just a database. So there's a lot of different kinds of data, right? There are things that are communicated better on paper or communicated better in a PDF or on a plan sheet. Other things you really do need to be putting into a database. You need your data accessible at the speed of relevance. So if you are, in the case that we were on Wolf Creek, when we had one time where we had a showing of slurry in our headwater, that was a really big deal because that could have indicated a major problem in the excavation. We were able to assemble the data very, very quickly in 3D space, put it in our CAD program, look at it in our GIS, and say, okay, that's not likely the problem. We were able to troubleshoot exactly what happened based on all of the project data and having it right there, right then. Because if you don't have it right there, right then, sometimes you may be guessing. Other things we needed to look at on a much more extended time scale, and we did. So you got to think about how fast you need your data. Telemetry and accurate information can be crucial, right? If you've got if you've put in instrumentation, but you cannot read it fast enough to know that you need to do something because that instrumentation is reading a problematic, giving you a problematic reading, you definitely want to be thinking about that. So, and you also want accurate information, right? We don't want you don't want to set your thresholds too low or have a situation where you're like, well, I kind of know. You need to understand the accuracy of your data and what it can tell you. Paper and files are just not enough anymore. It's probably the theme of the entire talk. You need to keep your database and use it to distribute the data to the right people so that everybody within your project that needs to know something can. You need to keep your data organized. Even a not well thought out organizational system consistently used can be better sometimes than a perfect system that nobody actually uses that way. Digital chaos happens fast. We all like to organize things our own way. Think about it on your projects, about how you want to organize that. Keep to that structure. That structure will actually help you. And definitely talk to people who have done it before, right? You're not alone in this effort. If you've not actually taken on this kind of thing on a project before, lots of people are working on this. We have folks within a variety of government agencies. Obviously, you're going to hear some more about some folks who are involved in this now. There's folks out at AE firms. Talk to any of us that have done it before because we love to talk about this stuff and we're always happy to help. And finally, just one final thought, please do not let the perfect be the enemy of the good. The hardest part is getting started. The hardest part is getting started. The hardest part is getting your data organized at the beginning. Don't worry, it sounds scary, but you can do it. So let's get out there. And do we have any questions if we've got time?
Well, what we'll do is wait to the end to address questions, but certainly, you know, if you do have questions for Vanessa, please write those down or use the Q&A pod that we have available. Vanessa and the other speakers will be keeping an eye on that pod, and we can address those through that chat, or we can, there may be some that are worth discussing at the end as well. So thank you very much, Vanessa. Excellent presentation. Our next presenter, and I'll let David go ahead and load up David is a colleague of mine with the Resource Center. David has been with the Federal Highway Administration for 27 years and is a senior construction and project manager engineer providing national technical assistance to FHWA and its partners. He's currently leading the FHWA's Everyday Count 6 digital as-built initiative. As such, he's leading and supporting efforts to effectively deploy BIM for infrastructure and asset management, including 3D engineered models, digital project delivery and inspection, and construction automation, as well as deployment efforts in alternative contracting methods and or such as design build and CMGC. Dave held various engineering and leadership positions in 9 states and is a professional engineer with degrees in civil engineering from the University of Florida and Purdue University. Dave, you have the screen.
All right. Oh, whoops. Can you hear me all right, Ben?
I can.
Okay. All right. So thank you all for having me today. And I appreciate Derrick, Ben, as part of the A-GaME, connecting up and doing some cross-linking with this digital as-built effort that we are going to be promoting during EDC 6, Everyday Count 6. I think this, I just want to say this is really just a continuation for us of a move to digital and how federal highways can support that move to digital. So appreciate that we get the opportunity to share that with you today. So digital as-built are really just the end of the process. I think really what I want to try to start out with as we kind of get into this presentation is that and really Vanessa's presentation was really impressive. It looks like we're going to need to connect with the Army Corps on some of the ways that they're doing the organization of their data and so forth, and see what we can transfer into our transportation world. But really digital as-built is the name.
David, sorry to interrupt, but we're seeing your presenter view rather than the full screen view. If you could head up to the top and display settings and swap monitors up on the toolbar up there.
Whoops, how's that? Whoops.
Very cool. Thank you.
That worked?
Yep,
it does.
You're set.
Okay, sorry about that. As I was saying, digital as-built is the title of our Everyday Counts initiative, but really it's just a continuation of 3D engineered models to construction that began in early Everyday Counts, and then e-construction, unmanned aerial systems. And then in the bigger scheme of things, it's what we call building information modeling or building information management, where we look at a life cycle of managing data for a particular asset. So, that really, I'm going to try to make that point as I go, but really that data accumulates not only during the project delivery process, but also, during other phases, and I'll try to make that point here in just a minute. So again, thanks for the opportunity. We know that having this information, much as Vanessa said, having digital information in a digital format is only going to help us to leverage the future. There are incredible technologies coming along. Data will support things that today we only dream of, if we can organize it and collect it in a way that can be durable over time. So I guess really what is usually, I start with a what are digital as-built, and basically what we're saying, digital as-built is a term that connects with the way we used to think of as-built in the transportation world. It's at least the plans marked up with what has changed. But really, the future will be something more like a project information model or an asset information model as defined by AASHTO, and it'll be a living record, updated in the case of this initiative, Digital As-Built, updated during construction, but for the purposes of effective life cycle asset management and performance management. And then, you know, as I said, it'll also be used during the course of the delivery of projects that, you know, much as Vanessa shared with her projects, but also, you know, with our transportation projects, things like automated machine guidance, constructability planning, and things of that nature. And I'm sure there are geotechnical uses that I am not as familiar with, but this group would be familiar with. So this slide is to really try to put it in context, kind of where we are going in the transportation side, and that is this idea of, you know, this life cycle, asset data life cycle, and keeping that data managed in such a way that it can be collected when needed for a particular business need. And so, you know, on the top right, you'll see the project delivery side where, you know, we're going to collect information during scoping and surveying. I believe that's where geotech information is often collected. And then we're going to put that in, you know, make that available to the data pool in as real time as possible. I like Vanessa's term of the speed of relevance. And then, you know, we're going to continue to add data throughout the project delivery. And then it's going to, you know, be updated during construction to create this as-built, so that as we hand off the information post-construction to operations and management and asset management, it's accurate, and it will allow them to do their job better. And, you know, I think you heard, I couldn't have asked for a better intro than some of the information that Vanessa shared. So digital as-builts is just a place where we can collect the constructed, you know, update the constructed information, and that would include, you know, geotech, and then pass it into operations and maintenance. So, and one thing I also want to mention is that often on the engineering side, we're working with proprietary software where the data is kind of bound up in ways that is currently more complicated to use. But, you know, what we're looking to do are to adopt data standards that will, like DIGS. I think you guys have talked about DIGS, you know, as part of your A-GaME, and schemas that allow us to extract information from proprietary software, put it into or bring it into a data pool or a model view definition is what's called, that supports a particular business case. You know, so it's not just data for data's sake. It's driven by business needs that, you know, are throughout the life cycle of an asset that help us to manage it with data-driven decisions. And it will also, I think it's already happening, but it will also help us with automation in certain areas, like in the field construction of a road. We have automated machines that, you know, are guided by the 3D design model, for example, which makes the work incredibly more productive. This slide is just to kind of highlight that, you know, what we're, a term that many people seem to resonate with is the idea of having a digital twin of our highway system. And so it would include the data elements, again, that we feel are important for any point along the process, whether it be during the delivery or, you know, that we save that data for later because we might want it for forensic analysis or some other you know, asset management functions. But, you know, the idea is, and to reinforce, you know, what Vanessa said earlier, you know, it's the ability to have that information be geolocated and to be visual to us. And if you can imagine using something like this to solve problems with your team, or to, to explain things to the public, which is often something we need to do, it is just incredibly valuable to be moving toward this idea of a digital twin. In addition, we have likely the probability that we will they will be looking for our asset information, certain aspects of it for automated vehicles, and to help them navigate, as a backup. So there's just so many things that we are on the cusp and ready to do. And really, I think for this audience, the point is that, hey, you're not alone. Other other disciplines are collecting their data. They're trying to learn how to manage their data. And I will talk about that in just a second. But the types of data that might be included, at least I think it's kind of an open opportunity. It could be unlimited, depending on what's important to an agency. But these are the kind of things that either we currently gather or we expect in the near term. If you'll notice on the left side, I think it's obvious we want geometrics, what the alignments of the road and so forth in 3 dimensions if possible. And then what we're currently not getting is, for instance, if you look on the left, utilities and subsurface. And so we cover that up, and then we spend a lot of money to find them again. Sometimes we find them with equipment that we wish we hadn't found it that way. It's just an incredible opportunity. And I added geotech after some conversations with Derrick and Ben on the bottom left, because I believe that's yet another piece of data that is just invaluable going forward as part of an assets management. So I wanted to try to use a graphic to, again, make it a little more, picture worth 1,000 words, right? So currently on the left, we collect 2D PDF or plan sheets, and we mark them up with unintelligent, markups, just a simple PDF that can't be queried or searched. And where we're trying to, they're paper or image based. Where we're trying to move is data-rich digital as-built that are represented on the right, where hopefully you would have a 3D design model that would incorporate, as you can see in this picture, both above the surface and subsurface information, and that you could click on that information or click on those graphics in order to get more detailed data and visualize that in a way that helps make decisions and avoid, like even during construction, allows for clash detection and things of that nature. So so that's kind of the what of digital as-built and some aspects of digital delivery. The why is, I think, somewhat intuitive, but really that ready access to data, it's just the opportunities are probably unlimited as to what we can do when we have data that we trust and we can visualize it. I think we're going to see enhanced safety, which is very important to us. Just in the safety alone from just not having to go out and recollect the data over and over again and put people in harm's way, particularly in the construction field where I work. Streamlined delivery, we're expecting that digital information is going to allow us to streamline workflows. We'll do business differently because now data can be passed more cleanly between the places that need that information during design, construction, and contracting. And then, we'll make better decisions, data-driven decisions. More detail that might resonate with, DOT folks, that digital delivery process that creates a model during design and associates with it all the information needed to build the project will allow us to, if we carry that into construction management, is allowing us to automate and you know, make decisions faster, much as was mentioned earlier with some of your geotechnical data. And then if we pass it into operations and maintenance, that data, it's used there as well, improving asset management functions, and then ultimately improving project scoping for the next time, because instead of having to search for all this information and try to, you know, pull it together, if we are organized through a data governance process, then we will be able to make future decisions with that information when we come to scoping again, and actually even through any of this process. So really, digital as-built is the end of a whole digital delivery process. And you know, I guess one of the things that's happening now that I want to mention, because it maybe connects more with the geotech work that you do early on, and that is, I think if I didn't mention this, several states are using the 3D model as their contract document that passes to the contractor and into construction. And with that 3D model, they can associate information like boring information, geotechnical information, which, as you might imagine, reduces the risk that contractors might have as they bid, and we expect is only going to cause us to have better projects. And so that model as the legal document is a really strong move right now within the transportation world, and I think we're going to see that create profound changes in how we deliver projects. I guess the point of that slide was that we're looking to collect the data once and reuse it often. That's just kind of a catchphrase we're trying to adopt, and that would be geotech data and all this other data. So I think Vanessa really made this point well, so I don't want to dwell on this other than to say that the lower curve here represents how we are currently collecting and recollecting and losing information from phase to phase, planning, design, construction. What we really want is to stop that loss of information and get on this upper curve of life cycle information management, which saves big dollars, as was mentioned, and really just makes us more effective. I wanted to just talk a little bit about the state of the practice in the United States, what we have seen as we enter digital as-built for EDC 6. What we see is, I guess some states are still using paper for as-built. Some are paperless, but it's image-based, so it's not digital information. And then if you can move to electronic at a minimum and collect that information, or preferred, if you start moving to digital, that information will then be put into file types and data types that are more easily extracted to be used together and analyzed together. So that is our goal with Everyday Count 6, is to help states consider how to move to that digital point and to govern their data. That's a term that's we often hear used, so that every discipline in the life cycle understands how the data is going to be collected, what is their role in keeping it accurate, and then how, what are the business needs that will drive the the collection of the data and management of the data. So this is just a slide I like to mention, that it's not just the technology on the right that helps us move innovation along. We also have to think about other areas of change management, such as people and organizational change. Sometimes IT can be a challenge. I don't know if Vanessa found that with the Army Corps, but many DOTs the IT is that is required is really challenging for them. And so, whatever we can do to work, in these different areas to basically, adopt a more advanced change management philosophy toward digital is what we are aiming, and also the processes and the workflows, and then of course the tools and the technology. So I guess just this slide is primarily just so that I can tell you that with EDC 6, we will be supporting states that want to move toward digital as-built. We have this NCHRP document is kind of like a foundation of where things have been. And so, we definitely look forward to helping your state and the industry that partners with us toward this. Currently, it looks like we have about 29 states that are interested. So I think the sense of digital is clear, and the desire to move that way is clear, that these states want to move toward that digital as-built place. So with that, I'm going to close. My contact information is here, and I guess I'll hand it back then to Derrick, I believe.
Cool, thanks, David. We really appreciate the overview that provided of EDC 6 and how the A-GaME and EDC 5 can fit into that framework. So thank you much. A quick mention that recordings of all 10 webinars, including this one, will be available soon. We're still in the process of putting the finishing touches on the archival website, but information will be sent to our emailing list in the very near future. Our next speaker today is Stephen Toliver. He's been with the Ohio DOT for 18 years and is currently serving as an assistant administrator in the Office of Geotechnical Engineering. He is the head of the roadway and geohazards section there, and he's the manager for ODOT's Geotechnical Data Management System. This system includes Ohio DOT's geohazard inventory data, historic geotechnical information, and data from the past 90+ years of information in the field, active project lab data, and now DIGS compatible data. Steve? You might be on mute.
Now you can probably hear me.
Yep, much better.
Okay, great. Sorry about that. Yeah, this afternoon I'll be talking about DIGS from the perspective of the Ohio DOT, our past, what we're doing at the present, and then what we see as our future needs. So first of all, I don't want to take too much time covering the background on DIGS. It was discussed last week in webinar 9 in Louisiana DOT's presentation. But for those that aren't familiar, DIGS is the data interchange for geotechnical and geoenvironmental specialists. It's basically a standard schema for transferring data inside your organization or between you and your consultants, or perhaps between you and other government agencies, or academia as well. So ODOT's been involved with DIGS now for 17 years, hard to believe. We were part of a group formed back in 2004, along with FHWA, and from that came a pooled funds study that ODOT led that went from 2005 to 2012. There were really two outcomes from that pooled funds study. One was DIGS version 2.0 alpha, and then also a proposal for implementation, with the idea being that would transfer it to the ASCE Geo Institute, with the intent of making it more available to the community so that we could get to more widespread adoption. So the history of DIGS at ODOT goes on from there. We did initiate a contract with ASCE to transfer both the DIGS schema and the data dictionary ownership over to the Geo Institute. And also during that time, we went from DIGS 2.0 alpha to DIGS 2.0. And if you go to the Geo Institute website, which I have linked there, you'll see that actually we're now at, I believe, DIGS 2.5 alpha. So development continues as we move forward. So I took this graphic from from the Geo Institute website. And as you could see here, there, the idea of digs is that you'll be able to exchange data through all the different, whether it's field, lab, analysis, presentation, you'll be able to pass your data seamlessly. Today, just because limitations on time, I'm going to try to focus a little bit more on presentation and then into our GIS platform, as I feel like that was the first area where we saw financial gain, cost savings to the department. So I wanted to try to focus on that. If you're a DOT that's maybe just you've heard about digs, but you're not sure exactly where you could get started and actually show achievements. So right now at the Ohio DOT, 90% of our data is being reported in GINT. That's going to probably change in the future, and I'll talk about that later. But like I said, as of right now, in January of 2021, we're seeing 90+% is in GINT. So because of that, our first step was to look at, okay, we've got all these GINT files, and again, we manage everything project by project. We have project files for each individual GINT database for each project. We contracted with data forensics and looked to create a conversion tool so that we could be able to take our GINT files and convert those over to digs, because then you have an XML that again would be sort of the first step of being able to transfer data. So using the Kinetics Digs feedback tool, which I'll mention is available on the Geo Institute website, data forensics mapped our GINT library, our template over to digs. And that was, like I said, that was our first step. The second step of the process was, okay, if I'm given a XML file, how can I convert that over to GINT? And that was sort of the second step of it, more or less making a round trip. The idea that you then can either accept an XML file from, let's say, a consultant that maybe is using a different type of software for their reporting, or if you needed to exchange data with them, you can also do it. So that way you've completed sort of the round trip, so to speak. So the nice thing about, and David touched on this, one of the challenges with implementing, things like digs is the IT challenge, at least it probably at most DOTs, certainly at the Ohio DOT. The nice thing about how we convert our files from GINT over to digs is that we're able to do it inside Excel. It's a simple add-on that you can load to your C drive or a network drive. It doesn't require any installation by your IT staff. And as you could see, for an individual GINT file, and again, that can depend, when I talk about a project, that could be 2 borings, that could be 72 borings. It averages about 2 or 3 minutes, the entire process, taking it from GINT over to XML. The round trip, basically taking the XML back to in our case, back to a GINT file, takes about the same amount of time. The only differences there are that it does require, we do it within GINT, and it does require connecting to the data forensics cloud. And again, that can obviously complicate things from an IT standpoint, but it again only takes about 2 or 3 minutes. And again, then you're able to accept an XML file in and convert it over to GINT, which is still our standard within the Ohio DOT for reporting. What we found as we've converted files is that from a standpoint of data, we're able to transfer it successfully. Whether you're talking about gradation, Atterbergs, data transfers without issue. Where we are having problems is with regards to text. From a standpoint of, we have consultants that, because of the flexibility of GINT, they've customized our library, or they choose to enter the data a little different, or they, in some cases we have consultants that are using GINT for their invoicing. So as a result of those changes, the modifications they make regarding text, we sometimes don't get all the text across. If you were looking at a boring log, prior to converting versus a boring log at the end, the data would be there. But sometimes, like I said, sometimes the text, some notes, things like that may not carry over. We've been working with data forensics to try to optimize that as we go forward. So far since 2019, we've converted, and this number actually is a little bit higher now, but we've converted over 450 projects, and that's a combination of generate data that we're generating internally as well as consultant generated data. So now we've got all these files. Well, the question becomes, okay, what are you going to do with them? And for us, that began with looking at our, probably from a dollar standpoint is our biggest asset, and that's our historic geotechnical information. Vanessa touched on the cost, of recreating for a single project. Back in 2004, a study was done, and at that time it said that if Ohio DOT, and at that time all of our records were basically stored in a warehouse, probably like a lot of other DOTs, if we lost all that data or information and had to recreate it, it was going to be about $500 million. Probably today with inflation and another 15 years worth of projects, it probably is now closer to $700 million if we weren't able to, to basically retain the information and data. So that comes out to be about 270,000 borings from 21,000 projects for the last 90 years. As I mentioned, 75 or 80, the first 75 or 80 years of that was all in hard copy, had to be scanned over to TIFF format. And then from that point forward, we tried to collect everything. It was still information, but we were trying to collect it in TIFF images. So then at that point, we had probably, give or take, let's say a little bit over 1 million TIFF images that had geotechnical information that we wanted to get into a GIS platform. So that led to a manual georeferencing effort, as we called it. And what that entailed was taking these historic plan images, these TIFF plan images, and overlaying them on aerials to create a best fit. And then from there, establishing the boring location points. And what we found, and again, as I cautioned earlier, every project has a different, different in size, but overall it ends up being about 70 minutes per project to get the information into GIS. Here's an example of a 1965 plan sheet. And this is that same plan sheet being in Arc Pro being manipulated on top, overlaying the on an aerial, and then the red points you see on there are the boring locations. So again, like I said, this process, for a large project can take, in excess of a day. For a smaller project, you're probably looking at, again, like I said, the average ends up being 70 minutes. It's always going to be at least 25 or 30 minutes, even if you just have a couple of borings. So we needed to find a solution going forward. And for us, DIGS, presented us with an opportunity. Our tech services group, with no geotechnical background, took a look at the XML and created a Python script to basically extract some ID and some geolocation data from the XML file. So some of the examples of that extracted data, things like your project information, your county route, your mile marker, if you have an internal tracking number like ODOT does, and I'm sure a lot of every DOT does, your boring ID, your coordinates in Latin long. So again, information that like I said, was could be easily extracted. Here's some examples of that data within the XML. If you look at an XML, it's tough to figure, to identify much in there. But again, if you can narrow it down to just the data that you're seeking, you can find, again, information like the county, the boring ID, the coordinates, and then also the top of the boring, if that's been surveyed. So here's an example of our transportation information mapping system. This system is a planning tool used by ODOT for all disciplines. From a geotech standpoint, it has our retaining wall inventory information in there. It has our geohazards, our landslides, rock slopes, and abandoned underground mines. It also has all 270,000 points of our historic geotechnical information and data. So in this particular example, I'm in Ross County, southern central Ohio. This is a project that hadn't been built yet, so the aerial doesn't show the eventual construction. I've selected a point, and in the past, we would just be able to show the boring log and perhaps some of the two-dimensional drawings that either Vanessa or David had mentioned. But now, in addition to all of those, you also have the ability to retrieve the DIGS file in an XML format, and then from there you can use that data within a variety of ways, depending on how you want to use it. So for us, that was the, like I said, that was the first step, taking our data and getting it, being able to show, a benefit from digs. So now from that standpoint, what we're able to do is we've been able to save 55 or 60 minutes a project, getting that data into our GIS platform, which ODOT averages, give or take, around 200 projects a year between us and our consultants. So obviously that's a pretty big savings if you can save in upwards of 200 hours of labor getting your data in. And admittedly, going forward, as we're able to go to more of an enterprise setup rather than looking at it project by project, there's a lot of opportunities to bring that down even further. So obviously that number will continue to improve. So where we see digs going at the Ohio DOT in the future, the first issue that we're going to run into is that while I mentioned 90% right now, we're at statewide in terms of us and our consultants in terms of GINT, we see a rapid move coming heading over to open ground. But in the case of the Ohio DOT, we might not be nimble enough to move over to open ground as quickly as our consultants. So we could end up in a situation, and I'm anticipating in the next 18 months, where 50% of our data is in open ground and 50% of our data is in GINT, with Ohio DOT internally being the generator of most of that GINT data and most of our consultants having moved to open ground. That's where digs will come in very critical, because we'll, instead of, and we've had consultants approach us say, we're thinking about moving to open ground. What are we supposed to do? And our response is, as long as you can produce a digs compatible XML file, we're perfectly satisfied with it. So that's, like I said, that is what we're looking at just from an internal day-to-day process. One of the big areas where I think this data will be used going forward is by university researchers. Don't have time here to go into great detail, but I did want to make sure I get a plug for the University of Dayton and their article in the January Geostrata, where they talk about, it originally started out as an artificial intelligence research project. And then we mentioned to the researchers, hey, why don't you try to incorporate digs into it? They did, and like I said, I would encourage you to take a look at the article in the January Geostrata. From an internal effort standpoint, we are trying to get the data into our internal design spreadsheets. We have an intern that tries to work on that from time to time amongst their other duties, and it is something that we're trying to pursue, because we think that we can gain benefit from that. Also want to mention, on a larger design build project, the example I think last week from the Louisiana DOT, there's an opportunity when you have the data in digs, you have opportunities to be able to take that data and do a lot with it, and creating tools. Even if it starts out as just being specific for that project, it then can grow into something that you can use more on a statewide basis and repeatedly use. And then finally, the thing that I think from our standpoint, we feel like is the real area where things really need to develop. And I would encourage every DOT, wherever you are on the, in adopting digs, every time you have an opportunity to talk to a software developer, whether it's that they want to give you a demonstration or you're able to attend a webinar, I would encourage you to ask them, what are they going to do about digs? What are they looking to do with digs? Because I think that is going to be where we're going to see within the industry the biggest benefit from digs is once we start to see our design software have the ability to accept that data in. I think that's really where things are going to be, where we're going to see the benefit going forward. So with that, if put any questions, feel free to put those into the chat. If you're viewing this later on from the DFI website, I think Derrick will probably mention that at the end, that all the webinars are going to go up there. I would encourage you, feel free to email me in the future at my email address there, and if you have any questions regarding Ohio DOT and digs. Thanks.
Excellent. Thank you very much, Steve. Great presentation. Yeah, and digs is going to be revolutionary, I think, in our industry, certainly in the context of what we're talking here in the digital age. There's certainly more to come on that, and we'll give a teaser here at the end on that. Our next speaker, and Scott, you can go ahead and load up your presentation. Scott Anderson is our next presenter. Scott is a principal geotechnical engineer with BGC Engineering. He is the co-chair of the TRB section subcommittee on geotechnical asset management. He's also a member of the National Academy's Committee on Geotechnical and Geological and Geotechnical Engineering and Steering Committee, or COGE, member of the Geotechnical Extreme Events Association of the National Science Foundation. He consults regularly with state DOTs, FHWA, and pipeline, water resource, and mine industry areas. Scott was previously with FHWA as a national leader within the Resource Center, a leader in federal lands, highways in Colorado, and a senior consultant engineer with URS. And he was also an assistant professor with the civil engineering department at the University of Hawaii. Scott, you have the screen.
Hey Ben, thank you very much for that. Just to confirm, is everyone seeing my title slide?
We are.
Excellent. Hey, well, it's great to be here and great to have the lead in with so many excellent presentations. My job here today is to talk to you about data visualization and in particular augmented reality, or something called mixed reality sometimes. And everybody on the slide that you're looking at right now is wearing a Microsoft HoloLens. This is a tool that allows them to bring something new into their reality, which is why it's augmented or it's mixed. You can see that, well, first of all, the lens that they're wearing, this kind of, I was thinking about this as we were talking earlier today, the master name of the whole program we're here for is something called Every Day Counts. And we forget that's urgent, and that the advance of technology is urgent. And this tool that these folks are wearing on their heads was brand new when the A-GaME technologies got started, and it's now about as novel as a flip phone, because it's been replaced by something that's a whole heck of a lot more powerful. But it is still quite a powerful tool that these folks are wearing. And they're looking at two different projects that are in different corners of North America. And really what's different about the two images is that the folks on the left are still seeing some value in data presented on a plan sheet. And so they're casting their gaze upwards at a hologram that's in their workspace or down at the plan sheet and making the best interpretations they can of the data that are there. Whereas the folks that are over on the right, they've rolled up their plan sheet because it doesn't do them any good. Their data are three-dimensional, as all data are in our business of geotechnology. They've rolled up their plan sheet and they're simply looking at the 3D visualizations. So this plan and profile sheet that's on the screen here might make you feel comfortable, and it might make you feel good. It makes me feel comfortable. I've seen 1,000 of these, and I think I have a pretty good idea when I see one what's going on. I've got a abutment to the south and an abutment to the north and a stick log underneath each. And it tells me a story. Well, part of the problem here is that this stick log is represented underneath the abutment at this location here. This stick log is actually this boring that's up here. And there's other holes that are shown in the plan view that are cone penetrometer soundings that aren't reflected in this at all. So this clearly is not an accurate representation of what's really going on at this location. So comfortable is not always best. This might make you feel a little uncomfortable because you've not seen it before, but this is me looking through a HoloLens at an embankment and a cut through a ridge. And my gaze is focused right now at this place called elevation 541.5 on the hillside there. But realistically, what I'm seeing is the CAD template for the embankment construction and the roadway cut. And I'm seeing the geophysics, the seismic refraction that was conducted along the spine of the ridge before this project was constructed, and also a boring that was drilled from the spine of the ridge that shows me things like SPT end values. The green being here is the percent recovery. And in 3 core runs, there actually was a measurable RQD. So that's shown kind of the red color right here. If I cast my gaze over to that spot, the actual values would show up. This is not a cartoon, but rather a digital twin of the project as built, as David was talking about, and is the data that are captured for this project. In the background, you see a bit of a legend. I could turn on and off some of these things, but these data are all available for this alignment. The ground is green here, not because it's a pretty color, but because it's the geologic unit. So that tells me something about that material as well. This is a little bit different visualization. This is a fault trench that's been excavated to look at the age of last activity on a fault near a project site. And this was excavated. The green, the ground surface is right along the top here. And samples were taken at all these yellow spots to do some charcoal testing. But long before the charcoal testing comes back, this trench will be backfilled. But these folks will always have this trench to look at in the 3-dimensional format and see where it is that their samples came back, what they told them, reevaluate their interpretation of something as important as whether or not there's nearby seismicity on their project. So how does this happen? Well, I'm going to tell you a little example right now. This has all, again, happened in the time that we've been promoting the A-GaME technologies. But the way this happens is today is that somebody goes to the field like this and they see something interesting that they'd like to share with others and communicate. So they pull out their latest iPhone or iPad Pro, and using the LiDAR scanner that's on that piece of equipment, standard equipment, they start scanning the outcrop. They get a 3D surface like this. Alone is pretty interesting, but it's also been taking a picture, and so that's called texturing. So in this case, the image, the photograph, is the texture that's put on that 3D model, and that's what you're seeing right here. So you can zoom in on it. It's all kind of interesting again, and look at it in this way. You can play with it on your iPad like this gentleman's doing here. But moreover, you can upload it right to the cloud. And once it's in the cloud, is this happening here? It can be visualized using a 3-dimensional augmented reality. And this is the new HoloLens. And anyone connected anywhere in the world to the internet and having one of these devices can go on to a piece of software, and within an hour of that photograph being taken, can be looking at the same thing in a 3D hologram wherever they happen to be. And they can drag this hologram around, put it in the right spot, but it doesn't actually have to be moved that much because you can walk around it. And because you can see things too while wearing these lenses, you can avoid the conference table there, and you can start looking at it. Now, as these folks are looking at it, you'll see some other things in light purple in the image there. These are people that are thousands of miles away in different time zones, and they're actually looking at the same 3D representation of that surface as the folks in this conference room are. And there's directional audio on these devices now, such that when somebody on the left of you is talking about what they're seeing, they sound like they're right to your left, and they're pointing. You can see what they're pointing at with their hands. You can talk about whether there is or isn't offset on that bed of sand right there. And when it's all said and done, you've got a very clear understanding of what's going on. If you wanted to take a 2D photograph and upload it somewhere, you could do that, but there's no need anymore. This is a little bit different of an image, and it's also a fun one for me to share with you today because this is from the very first EDC5 summit in Baltimore. And it's 2 gentlemen, at least one gentleman, standing below ground looking at a bridge site. And they're looking at data that are textured as well. There are certain objects here, and the objects are cone penetrometer soundings, piles, seismic refraction work, and SPTs. And the texturing here is not texturing of the ground like the image in the last things we looked at, but rather it's a data value. It's something that we measured from the ground. but it's still applying a texture to an object. And there's lots of fertile ground for thinking of the best ways we can do this in the future. But that's what these folks are seeing. The image isn't of the highest quality because it's actually a person sticking a iPhone up between their cheek and the lens and taking a picture through the lens. So it's exactly what you would see if you were wearing these things. Now, these two folks could be, like a junior engineer and a senior one, talking about how do they, what do they make of these data, sharing some judgment. It could be a geotechnical engineer and a project manager talking about the value of collecting additional information, or it could be the owner and a contractor talking about what is known and what is not known about the subsurface prior to beginning work on this project. And so you can see them in the space. It's also possible to black out the background and make something more vivid, like you see right here. But you lose people, and losing people is losing some ability to communicate. I mean, it's like me talking to you on a webinar instead of us being together in the same room. But you can also snap an image and put it in a report if you need to resort back to a 2D kind of framework, and that's what is shown on the screen right here. Same data, different format. These data right here are from the great state of Ohio, and as such, they're available in a DIGS format. And so we're looking at data here that includes seismic refraction, electrical resistivity, SPTN values, recovery, and RQDs again. And this, it could be something like let me actually say that the data, it's possible now that these are data-driven processes too, so that it doesn't take long. It takes a little longer than Steve was talking about in terms of populating these logs from GINT logs into this visualization, but it's on the same kind of order of magnitude. Another really interesting thing about looking at data in this style is that we're looking at, it looks a little, you've never seen it like this before, so it looks a little blurry, but you're seeing electrical resistivity results in the same view and time as you're seeing seismic refraction. In other words, you get for the first time the ability to evaluate something that has a low resistivity and a high velocity, or vice versa, or in contrast. And it really gives you new ways to interpret the data. So to talk a little bit about the, that was kind of DIGS, and I want to talk a little bit about the digital as-built idea and another A-GaME technology, the optical televiewer. This is a project, and I think this little video clip will someday be on the FHWA site for all this, of a Manning Crevice Bridge as it was built. At each one of these white flags over here, there is a boring, and each boring had an optical televiewer for its full depth. Because this is a cute little movie, we're just going to look at one of these, and we'll go underground, and we'll see that log. We'll also see the interpretations that the engineers and geologists made at the time this bridge was being designed, and that is that there's 3 joint sets, or 4 perhaps, that were controlling the structure there. And then this log, kind of, you just see it at like stick level. Normally you'd go right up close to that and you'd get to see this in a close way. But again, it's a movie, so we're pulling it out for you and bringing it forward. And you can look at this core, this synthetic core, but this is actually reconstructed from what was filmed inside the borehole at true scale. And you can move this up and down so that each foot is a foot. It would, if you had this on in your office, it would project all the way up through the ceiling and all the way down through the floor, and you could move yourself up and down the core to look at how open some of these discontinuities are and what values you're assigning to them and what kind of performance you expect out of them. And that's the kind of thing that is available today. Now the core is going back in the hole here, and these 4 different colored planes that are being shown are the interpretations. So right here, you have data, you have interpretations, and you have an as-built drawing of the bridge site. I want to go back and talk a little bit about people in the picture, and this is an example where we're communicating. So Here we got 5 people looking at a hologram. There's something new in this one, and that is the light blue you see at the top of the screen. The light blue is actually the water table, and it does fluctuate seasonally, and so the 4th dimension of time is readily visible today in these 3D models. It moves as you wish it to, and you can stop it at any time you want. But they're looking at different things, and the 4 on the left are pointing something out. And there's a sort of what I call the lone wolf over there on the right, and she's looking at things her own way. And it's important that people are able to, while sharing the same hologram, whether they're in the same space or not, they can be looking at it from the same perspective, or they can be looking at it differently. And it's when those things come together that I think we get the greatest understanding. Here's another example. You can see the hard hats in the box over there on the floor. These folks have come back in from the field where they literally had a hard time seeing the forest for the trees because there's only so much you can see out in the field, and when you come back and you can build this 3D model in the size of a hotel conference room, you can look at things that you couldn't see out in the field. I'm certainly not implying that the field visit wasn't valuable. It's just that this brings a new value to the field visit to come back and put it in this perspective. In the background, you can see an inclinometer plot, perhaps on one of those stands, and it's made really big, so it looks powerful, but it doesn't look near as powerful as it does in the 3D image that they're looking at, where they're actually seeing it move with respect to the borings and so on. So this is all available to them in this case. That was a pre-COVID type image. When was the last time anyone here was in a hotel conference room, right? So it's really been fortuitous that the developments in these areas have marched along nicely this year, and it's now possible to do everything that those gentlemen there were doing in remote settings, each person being in their own office and sharing a look at the same hologram. Here are a bunch of folks that are looking at a hologram. It's what we call a tabletop model. Everything on it is a GIS layer. So anything that goes on a GIS can be visualized in this platform. And it's one of the easiest ways to move data into augmented reality type space. You get several people. The person in the middle there, they made what's known as a Zoom mistake, leaving their camera on and getting up and leaving. I don't know what they're looking at, but once again, there is a person way off to the right looking at things their own way, and it will bring their judgment and their understanding together with those on the left, and will really help in getting a shared understanding together. And my point is, through all of this, is that once there is a shared understanding, there really is a great degree of risk mitigation because communication is key to all of this. The A-GaME technologies are all about getting data out of the ground, but just like anything else, it doesn't matter how brilliant you are. If you can't explain it, it's not of any value. So this is really about getting the value from all of the A-GaME technologies, getting it shared, getting a common understanding. I was going to close with the Hollywood ending to my story here today. Is that if you're not doing this now, it's because you don't want to. It's not because you can't. None of this is science fiction. None of this is in the future. All of this is being done. But some of the prior presentations today reminded me of something that's very real and that I have experienced myself. And that is, there is no place for this in the workflow. And this is a challenge. That this is, you might find this very exciting too, but you might be asking the question already, who does this and where does it fit in? And indeed, that is one of the challenges that we face together in moving forward. Just in closing, again, I guess I'd say that, the geotechnical professionals are unique in our project development business in that we are the ones who take 3D information and make it 2D. we have to ask ourselves if that's really the role we want in the future. Thanks a lot. And it goes to Derrick, I think.
Yep, thanks, Scott. Yeah, with respect to your closing, I think it's especially exciting to know that what you showed us today in your presentation, that these are technologies that exist today and are currently being used on program delivery projects. So in many ways, the future is here. Also exciting that most of the A-GaME technologies produce digital data, which can be imported easily into these workspaces. And that gets back to the presentation on digs. So thanks much for your presentation today. I'd now like to welcome our final presenter this afternoon, Alan Marr. Dr. Marr founded and leads GeoComp, one of the foremost providers in the US of real-time web-based performance monitoring of civil engineering structures, including dams, levees, deep excavations, retaining walls, tunnels, bridges, buildings, and utilities. Alan has extensive experience in testing to measure the mechanical properties of earth and materials, designing earth structures, and determining the causes of poor performance of geotechnical structures, while also developing cost-effective remedial measures for troubled projects. He's published widely and given invited keynote lectures around the world on topics in geotechnical engineering, performance monitoring, data management, and risk management. He's an elected member of the National Academy of Engineers and the Moles, and served 1 year as the president of ASCE's Academy of Geoprofessionals. In 2019, he was honored by the ASCE Geo Institute with the Seed Medal and delivered the Seed Lecture in Philadelphia entitled Geotechnical Judgment and Risk. Alan, looking forward to your presentation.
Thanks very much, Derrick. Can people hear me?
Yep.
Great. And see my screen, I hope.
Yes.
Thanks for the invitation, and Derrick, your request for me to kind of pick up on the Seed Lecture theme on look in a bigger picture at some of these tools and what do they mean to us in the geotechnical world. So I thought I'd talk about the importance of data to risk assessment and to engineering judgment, and kind of very quickly, can big data help us in this arena? I'm going to hit a lot of high spots here, just to provoke your thinking process a bit, I hope. So you heard Scott mention the word judgment several times, and the question comes always, how good are our geotechnical judgments, especially considering the large number of litigations that seem to be going on, many of which you never hear about because they're quietly settled. But I went through, when I was preparing the Seed Lecture, just my own knowledge of some of the major issues that I've had some association with in the last 10 to 15 years. And I tried to put some dollars next. These were ones with geotechnical elements to them. I tried to put some dollars next to the losses that were being alleged or claimed there. And these are big numbers. The failure of the Katrina flood protection system resulted in potential claims against the US government of over $60 billion, which I was involved in with the Department of Justice in resisting that, and we won. But these are big, frightful numbers to people potentially on the hook for some of these. And why do they happen? There are a lot of reasons, and I'll come back to that a little bit later on. But I just want to set the stage. Is there something wrong in our profession? And can these new tools that we have been hearing a lot about help us to reduce or avoid many of these things where things go wrong on the project? And as a part of all this is the whole question of big data. Something we hear a lot about these days. Can big data potentially, together with these other tools, help us to get a better handle on our projects and reduce the chances or the odds that we're going to face some of these very challenging failures or failure to perform on our projects? So just quickly, big data, you all probably have heard about this. You know, it's not just necessarily lots of data, but it's things that have high volume, high velocity, a lot of variety, so large it's very difficult to store, manage, process, and analyze the data using traditional tools. And for us as engineers, this really means you outrun the ability of things, the standard tools we use like Excel. And just, I'm not going to go through the bottom, but just how much information gets generated on the social media network every minute. 77,000 hours of video, for example, generated every minute by Netflix to stream out to requests. Well, how does that map over to geotechnical engineering? You know, and I just quickly put down some of the sources of big data in geotech. If you go back through the 10 sessions of this program, you'll see a lot of examples of this, and many of these new tools are producing large quantities of data. Just glance down through those. I'm not going to cover each one of them, but just typically, I thought it was rather interesting. I heard earlier, I think it was Vanessa said that her one project had 50 gigabytes of data. Well, I actually looked at one of my projects. Maybe that's a magic number, 50 gigabytes, and I've got another one I'll show you later on that also produces that much data every day. This is just the beginning. These are growing exponentially as more devices and tools come online. We're just going to be buried with this. What has brought this about? I thought it was useful maybe I'm an older person in this group. I've been involved with computers and technology ever since undergraduate days, but I've seen enormous evolution of things here, which I think some people lose track of, and especially how fast it's changed in the last 10 years. And so I just captured 4 things that are really revolutionary and will continue to evolve at amazing rates. Data acquisition at high rates and high reliability for very low costs is relatively new on the scene. Many of us that are a little bit older remember the days when things broke. You thought you were getting data, it didn't come through. And to be able to take readings once a minute was thought to be very good. And now we're getting megabytes of data in seconds sometimes. Storage of large amounts of data and processing that data quickly at low cost, essentially no cost for storage today. Communications, a really key part of this, allowing us to move data rapidly anywhere in the world, as Scott demonstrated, for little to no cost. And then reporting and conversation tools to get knowledge where it can be used through the internet and the sharing of files or even images like Scott demonstrated. Some of us today, the younger set particularly, tend to start taking some of this for granted, but these are really revolutionary, fairly new things that some of the older generation also may not realize just how much has changed, and just think of it as changing tenfold again in the next decade or so. How are we going to deal with all that? And what do we do with all this big data stuff? And it really gets down to, as engineers, what we're really interested in is answering 4 questions. What has happened? This is what we do for our clients. This is what we do for a living. What has happened? Why did it happen? What is likely to happen in the future? And what can be done to affect the outcome in a positive way or to avoid a negative outcome? And in the end, these are really still the basic questions that we as engineers have addressed for a very long time. We just have to figure out how do we use these new tools to keep focused on these questions and not lost in all of the glamour of the flashing lights and the whiz-bang stuff. Just as an example, hasn't been talked much about, except I guess Vanessa mentioned this a little bit, but the whole information data stuff coming from measurements is potentially overwhelming to us, or will become. Many of you know how important instrumentation monitoring is to geotechnical engineering, so we know how the actual project is behaving compared to how we expected it to behave or perform. But it's not just data from instruments. It's what I call context information. It's all of the other stuff that's related to what's going on in the project that is possible causes of what these instruments are telling us. So it's gathering all that information so we have the data and the context stored in some reliable way that's readily accessible in a format that the users can use when and where needed. And so we, as a company, have been, and others are doing this today, working on systems to collect this information from a wide variety of sources and deliver it out to devices in a form that you can quickly consume and use to make decisions, and do it without any special training. And so the tools have evolved today to do some of the things that Vanessa talked about relatively straightforwardly without much training on your smartphones. GIS delivered to the smartphone very fast, with you able to zoom in, zoom out, see data in the full history of records of massive quantities of information delivered very quickly. Here's an example just to put some basis to what I just said. This is the new Mario Como Bridge in New York over the Hudson River. And we had the good fortune as a company to design the structural health monitoring system, install it, get it up commissioned, and now maintain it into the future. And this is the wave of the future, I hope, in that why did we put 800 sensors on this bridge to measure all the key elements of performance? It was a key part of the designer's asset management concept for how he could possibly look into the future and assure that this project would last for its 100-year design life. And so one of the examples of that is corrosion sensors located in the deck of the bridge to monitor how fast salt intrusion may happen through the deck to get to the rebar, so they can time when they have to add a very expensive surface coating on the deck to slow down or slow up that salt penetration. This is where we're using measurements to help enforce real-time money-saving decisions. And just an example of how these data generate an enormous amount of information. Every day, the high-speed data loggers on this thing take 4 billion readings, amounting to some 50 gigabytes. You say, why in the world are you doing that? Why so much data? We take the data to capture events. We don't keep all that data. If nothing's going on, we discard it within 24 hours. But if there is something we call an event, such as an earthquake or a bridge, a boat strikes one of these columns you see here, or heavy winds blow the bridge, or a truck accident that hits part of the structure, we actually can go back and pull that event out of all those data loggers, and we know to 100 times a second exactly what's happening to every component in this bridge as a result of that event. But we don't want to keep that if it's silent. And so they're very smart intelligence in the data loggers and in the system here to reduce that 50 gigabytes down to something like 1 gigabyte per day that gets kept over time. That's an example of the challenges we're faced as we go into the future, and yet our ability to deliver highly valuable information, because in the end, all those bridge people see is just a few numbers on a screen every day to tell them that the bridge is working okay, and that if there has been an event, to which case then they can dive down to it. So back to the question, will the new tools and big data concepts stop the kinds of problems I showed on my second slide? In some ways, yes. But we have still, let's look at what causes accidents. What causes failures? And I'm not going to go through all these. I've listed them here. You can kind of look through them. But there's a lot of causes here that it's not entirely clear to me we're going to pick up with smart algorithms and AI routines. We might catch some of these, but unless we are programmed or thinking to take these into account as we develop these new tools, I fear we may add more problems and create more accidents than we're going to solve. They might turn into a different set of problems causing accidents. But I just want to warn us, those of you involved in developing and applying these tools, that beware, question what you're seeing, questioning the quality of that information and the reality of what's being delivered to you. Generally, incorrect judgments. If you look at every item that's on this page, it has its roots in incorrect judgments being made as a contributing cause to each one of these root causes of accidents. I wrote some time ago about the process of engineering, geotechnical engineering, and it's really quite unique in ways that it requires us to use a lot of judgment. And even as we develop these tools, as Scott said, these are tools to help us better exercise our judgment. So judgment remains very important when we characterize the site, when we set up our model to do the analysis, when we come to designs, we make all kinds of decisions on the design part of things to simplify or make things that can be built and constructed. And then as we observe the performance of the actual construction, again, we make lots of judgments about, is this performance okay? Are the surprises we're seeing still acceptable, or must we do something to tweak or modify the design? So this judgment role is really critical. And it's still something where we talk a lot about, but we're having a hard time really trying to quantify it and figure out how we improve on it. And until we can do that, it's going to be hard for us to do that with these new tools, in my view. If we think about, how judgment works in our brains, we start on the left here with a set of facts, of which we're going to generate a heck of a lot more of those with all these new tools. We're going to be overwhelmed with data. And we put those into models and images. We do evaluation and make some judgments to come up with our mental model of whatever it is we're trying to solve. And from that mental model, we extract some conclusions and recommendations of how to go forward. We go forward, we make observations and measurements, and we receive feedback of reality, and we discover there's a difference between what our mental model was, mental image, or even digital image, digital model, and what reality is. We've got to make an adjustment and feed that back. These tools are going to help us with this, but they're not going to remove the need for us to constantly question our models, our designs, and what we're seeing for real performance, and improve on things, and also look for poor performance so in time that we can take protective measures if we need to avoid a catastrophic failure. So that brings to mind the question that's still going to dog us, I think, in the whole area of risk, dealing with unknowns. Risk is all about unknowns, things we don't know. If we know everything, we have no risk. And so you get into the risk world and people talk about the famous Rumsfeld risk characterizations of the known knowns, that is what we know, the known unknowns, what we know to be unknown, and the unknown unknowns, what we don't know. And that seems kind of interesting, a head twister on philosophical thoughts, but it's actually missing a couple of things. It's the misknowns. That is, this happens to us a lot in geotechnical engineering, where there's a lot of stuff we know, but we miss it on a site because we don't do a thorough investigation, or we don't apply the things that we should have applied because they're well known, so-called errors and omissions that happen on projects. Hopefully these new tools will help us quite a bit in this area, I'm hoping. And then there's the whole area called unknown knowns. That is the stuff that we should know, but we intentionally refuse to acknowledge that we know about it. We just don't deal with it. And this happens a fair amount too. Hopefully some of these new tools will put data in our face that we can stop this avoiding of things that we should know about. This whole thing of judgment, there's all kinds of biases in the human brain. This has been well studied in the last 30 years, and this was a subject of my seed lecture. Lots of biases that are operating in our brain that make it very difficult for us to give honest opinions all the time or come to honest judgments. I just put this slide up, and if you want to read more about it, see my article in Geostrata about a year or so ago. But these are things we have to each be very aware of. You're looking at all these new tools, you're looking at Scott's holograms, you're making judgments. Are you really making judgments free of bias of these types, of these sources? Because it can be very tricky with these new tools and all these images. We're moving much faster to quicker decisions, but are we stopping to be reflective, introspective, and challenge the judgments? Unsound reasoning also plays a huge role in all of this, and these are just kind of some of the things that go on. And as we generate more data, that doesn't necessarily mean we're better. We may just be generating more poor data or missing data or defective data. And I know all those working on these tools know of these problems, but are the ones that are going to wind up using these tools going to be cautious about these things? And one other couple more slides, and I think I'll be done here. As we talk about risks and judgments, one of the ways we wrap this up on a project is something called a risk register. And some of you are quite familiar with this, I'm sure. Others may never have seen it, where you're trying to identify what can go wrong and what's its consequence. And we really increasingly try to quantify these in terms of the likelihood of a risk event occurring, what its consequence might be in time and money, who might own this risk. And then something I've added to these we don't often see, something I call an emerging indicator, or something that we can measure that's going to tell us whether the risk is actually happening or not. We talk about probability or likelihood over here. In reality, this is looking into the future where we don't know, but in reality, in the future, at some point, this goes to 0 or 1. We would like to know that we've got emerging indicators of this risk early enough that we can get in and do mitigation. So another role for data to feed into this whole risk management process. This is a whole area I spend a lot of my time on. You know, how do we make measurements and observations of things to tell us about emerging risks? Risk assessments are only as good as the quality of the data used to make them. This is true. We hear it over and over again. Vanessa talked about garbage in, garbage out. True here too. Even though we're taking into account uncertainty, these are still numbers that we are using to try to get an overall assessment of risk. These numbers in this format are very hard to check and validate. And this is one of the shortcomings of risk assessment, but it doesn't stop us from going through the exercise of trying to anticipate what could go wrong in a project and being prepared to deal with it. So I'm hoping that some of these new tools that we're seeing too will help us do a better job of understanding the project, understanding the uncertainties, and improving our estimates of likelihood and consequence. The value of these risk registers really depends on our ability to detect emerging risk early and respond as needed to avoid the bad event from actually coming to fruition. So a caution on judgments, judgment and risk become, I'm sorry, I misspelled word, even more important with all these new tools and big data. I think the push is on to move faster, to deal with a lot more information, to rush through things faster because we're all expensive, and we got to be cautious. You know, there are certain shortcomings that we as human beings have that I'm not sure are going to be overcome with the bigger and better tools. We have difficulty thinking accurately in probabilistic terms, and we tend to underestimate consequences and make mistakes in using probability. This is proven through much research. Forecasting is hard to get right. There are people in literature ever since we started writing talking about it. Forecasting is fool's game. And yet that, as engineers, is what we do all the time. When we do a design, we're forecasting that we've done it right and it's going to work. So, but it doesn't always work that way. So again, we still need strategies in every case. Even though we got lots more data and very good quality data, we still need strategies to adjust to unexpected outcomes. We got to remain very vigilant to safety issues, to checking our work, to the cultures that we're working in and how they're interpreting these tools and the conclusions that recommendations that we're coming up with, and then what quick actions are available to us to address any of these issues. Well, caution, beware of innovative solutions, including some of these new tools, as they may hide great uncertainty underneath them. The pretty pictures may look great. They may help us make quick judgments, but if they have flaws in them, we may not see it because we don't see the underlying data. We're just seeing an image now. Finally, I would urge us that we should explain all biases that are included in our judgments and the associated risks that result from our judgments to our clients. They're the ones that ultimately need to make the key decisions about how to manage these risks on their projects, not us. And so communication of these risks to the client is really a key part and will become even more important as we go into the future to help as each projects get bigger and bigger and the potential magnitude of losses get bigger. And as we use these more tools and it becomes more difficult to do checking and validation of the models on which we are making these judgments. So with that, I'll stop. I really appreciate this opportunity, and it's kind of fun to participate in all this.
Great. Thank you so much, Alan. Great words of wisdom, great insight. Thank you all presenters, great presentations, and great lead into a very short lightning round discussion I hope that we can have before sort of closing things out here. You know, one thought, and I saw a number of points made about data quality and a question that came in on data quality where, you know, obviously DIGS does not deal with data quality at all. It's an exchange, you know, a transfer protocol. So in light of the fact that we are, you know, the idea of having this data available, now we need to have some type of confidence in that data to be able to use it and to put somebody's seal on it, as one of the questions came up. So I just want to sort of open it up to every one of you on your thoughts on you know, how to handle that aspect and how that's going to impact our work.
Vanessa, you're muted.
Oh, sorry about that. If I may, one of the first things you've got to take into account is it's the same question. How do I trust my boring log? I wasn't there. I didn't see the soil. I didn't handle it, right? We handle this in the same way. QA/QC procedures, make sure that you've got them. As far as the database goes, metadata, right? Who generated this data? Where did you get it? What time did you get it? And then you need some static data that proves to you so you can go back at any point and say, okay, let me just do a quick check. I'm gonna pick a certain percentage of my entries here and just make sure everything's fine. So when we're working on construction projects and a contractor is generating this stuff, just because they hand me a database, we're not done, right? I ask them for the raw data files so that we can compare them to the process data that we get. We will often ask for hard copy PDFs, basically, of static data, so we can actually take that and we can compare that to the database at the time, but we can also track it back later. So you got to have good QA/QC procedures. As with everything, how do you trust your data? Collect it right in the first place. Make sure you have a good, robust QA/QC program.
And I'd like to add to that too, because I'd say, the kinds of work that I was showing, QA is difficult, and we have been doing that, and because some of the early stuff we did for A-GaME and whatever wasn't real data. We weren't engineering with it. We were demonstrating how these tools are powerful at showing what's known and what's not known. But in the actual QA process, it is difficult, and we're doing it, but we can't envision doing it without what Vanessa just said. Like the geophysics, I have to still get the kind of hard copy so that I can QA what I'm seeing in 3D weird space at a few spots in a few different ways, and setting up protocols for how to do that. So it's not easy, and it has to be part of the process to keep going so that we have confidence in those 3D models.
So I'd like to add to that too, and I don't know if you all have the same experience as I do, but I have a real hard time with some of our younger staff, just in simple calculations, getting them QA'd. The modern world moves so fast, and they trust these tools so much, they don't see the value of it. And even though we've gone back to the old school thing of put a cover sheet on it and who did the work and who checked it, and it's very hard to get this done routinely. And it's when it gets done, you don't have problems. It's when it doesn't get done that you have a problem. So I think somehow we got to think about building into these tools some type of monitoring system in a way. Is the QA getting done, and is it getting done properly? Otherwise, we're going to get ourselves in a real lockup situation, I think.
Yeah, and data quality is always going to be an issue. We're never going to get away from it. But as you pointed out with checks, right, you can't trust a computer to do it. You're thinking for you. We do not yet have intelligent computers. We have very fast calculators. AI has got some promise, but it cannot replace your brain. Don't ever let it replace your brain. But there are some tools we can use to actually do some checking. There are some Python scripts that some of the young engineers and geologists that I worked with were writing to go find needle in the haystack, find some what's weird data for a human with an engineering brain, with a geologist brain to look at and say, hey, does this make sense? Or is there something wrong here? And so we can leverage these tools, but yeah, old school on this one, never let a computer think for you.
And teach our young people, all the way going back into school, those of you who are still in school, teach them to do checks of their work. We got to get those skill sets right from the beginning. That's a part of being a good engineer. I'm sorry, David.
No, that's fine. Yeah, I think in the grand scheme of things, if you've heard the term data governance, and I know Ohio has quite an advanced program, what that does is sets up a stewardship of the data in a way that not only checks the geotech data, but it checks, everybody is assigned to be a steward of the data based on a certain set of rules. And of course, it's QA, some of the things you guys talked about. And then that whole system creates a life cycle of data that is believable. And the other thing that I have heard, I'm not as savvy on this, but I know there are research efforts that take big data, and maybe it's artificial intelligence, I'm not sure, but they assess through the metadata, I guess I'll call it the accuracy of that data. So it still can use different levels of accuracy of data, but it knows that some of it is not as good as other. And I know that's kind of a bigger idea. You know, you guys are talking about geotech information, but I think that that is, you know, one way that I believe people are going to do more QA. Also, in my world, the visualization of the data allows you to see issues. So when you turn it into a 3D picture and there's something over here or something, you know, it's like it's one part of a quality assurance, is that you can literally see it. Whereas if it's just a bunch of if it's a table or something, it's hard to really understand. So.
Yeah, I mean, from Ohio DOT's standpoint, I'll just be real brief here. I mean, when we convert our data over to digs, we're either doing it on a consultant project where the project has basically been filed and has gone to sale. So at that point, it's been reviewed, you know, gone through all the normal reviews that requires. From the standpoint of our internal data, when we would convert it over, it's already, you know, it's been issued as a final boring log by our office, and then we make the conversion. You know, so from a standpoint of, you know, within our planning, within the TIMS, you know, I showed the screenshots of our GIS platform. We only certify the locations in terms of, we provide a confidence that we feel like, okay, this location, you know, we know that the boring was drilled there. We don't make any, you know, claims as to the data. You know, you can make an argument that a boring from 1964 might be more accurate than a boring from 1994. Again, that's professional judgment. We only provide the data as a planning level tool, and then it's the designer's responsibility what they do with it.
Very good. Well, thank you all very much. We are at the top of the hour. I do want to just sort of close out and thank everyone who has participated within this series for the past several months here. We've had over 50 people present or help us behind the scenes. So thank you very much. I think I am sharing this. You are seeing my screen, yes. I hope. Yep. Okay, very good. Well, thank you so much, all of you, over the course of this winter webinar series. Derrick and I think it's true, speaking for Derrick, you know, we had no idea just how good these webinars were going to be, and the quality of the content that's contained in these webinars. And so I am hoping that many people take advantage of these archived files. I very quickly just want to give an idea of what is headed in the future for the A-GaME. There's a number of things in the pipeline. One of the biggest parts that has to do with just the process of getting things pushed through and put on to a web-based platform or a website. And so a number of things are there. It's done. We're just waiting for the thumbs up or to get permissions there are a few of you guys out there who have presented. We need to have your release forms for DFI to post the archives. But there's MWD information, the geophysics web tool, which is the geophysics reference manual for FHWA that's going to be revamped, case histories, videos that you can share with people in decision makers and other areas that we need to convince that the A-GaME doing better site characterization has value. We have videos that can share that. I'm showing you a picture of the PP 102 AASHTO standard for digs. Look it up. It's coming to a DOT near you. So get familiar with that over the next several years. The intent is that will become a full standard. So this will become industry standard, and this is the start of that process. A number of other actions that are taking place. The AASHTO manual, we're almost to a point to ballot that is scheduled, targeted to be balloted in May. So after that, hopefully in the next 6 to 8 months, we'll have an official AASHTO manual on subsurface investigation that gives the means and methods and is consistent with the A-GaME principles. You may also be aware that there's work on translating coefficient of variation, or capturing, taking into account variation into our sites, into the design aspects on reliability, and T15 is working on that as currently. A number of efforts going out and outreach. We're going to continue that, showcasing your good work, and just looking for opportunities in the industry to present and share that great work. Any questions that you have? Oh, just one final point here. Please sign up. Hopefully you can see my cursor here. If you just do a search on FHWA A-GaME, you can find this link at the very bottom of the page. This is going to keep you in the know on what's coming up, when things get posted. Probably the best way to communicate. But always feel free to give Derrick or myself an email or a phone call. We'd be glad to talk with you and point you in the right direction. It has been a phenomenal webinar series. Thank you so much, everyone, for your contributions, and thank you for tuning in and participating in these events. Derrick, any final thoughts?
Well, Ben, if I forgot to mention, if you don't mind, that you guys are not alone. There is AASHTO has adopted a data schema for everything I talked about called IFC, and so we are moving to a place where data can be shared much more readily, even from proprietary sources. So
yeah, and that's the beauty of DIGS, is that it makes that go completely away, and it is open source code, so
exactly,
and expandable.
And I can see
a lot to do with that.
DIGS and IFC and maybe a couple others becoming the standard for highways, so that we no longer will have all those exchanges. The complication of that, it'll be much more data is much more readily exchangeable. So thanks.
Yep. Thank you, David. Thank you, everyone. Appreciate it. Derrick, are you still online?
I am still on, and as today's co-moderator, second everything Ben has said. It's been a delight to be with you over the 10 webinar series, and you will be receiving information on where the archives are located. Thank you again to all of our content providers and everybody who's watching real time and on the archive.
Thank you, everyone. Take care.
Thanks, everyone. Goodbye.
Bye.